Chapter 4, Lesson 4, Scientific Notation. What are you going to learn today? How to write numbers in standard form and in scientific notation, and then how to compare them, tell which are they equal to, less than, or greater than. So what is standard form? Standard form are numbers that do not contain exponents, for example, 100 or 156,234. Scientific notation is a system of writing numbers using multiplication and powers of 10. A number in the form of a times 10 to the nth power, where a is less than a, 1 is less than a is less than 10, and n is an integer. For example, 95,700 is standard form. 9.57 times 10 to the fourth is scientific notation. 0.000024 is 2.4 times 10 to the negative fifth. I apologize. So we use scientific notation to write really big or really small numbers. So remember, numbers that do not contain exponents are written in standard form, and scientific notation is to the power of 10. So here are some more examples of numbers in scientific notation. 3,500,000 would be 3.5 times 10 to the 6th, standard form, scientific notation. 0.00004 equals 4 times 10 to the negative fifth, standard form, scientific notation. Express each number in standard form.
Let's use standard form to solve the following problem. Express each number in standard form. 1 8/10 times 10 to the fourth power. 1 8/10 times 10 to the fourth power. To put this in standard form, we want to first rename 10 to the fourth power. And 10 to the fourth power is the same as 10,000. That's 10 times 10 times 10 times 10. Now we'll multiply. A helpful shortcut to multiply is recognizing those 4 zeros. They represent 4 placement movements of your decimal point. Watch. 1, 2, 3, 4. And when you multiply that way, you get 18,000. With each movement, we've represented a 0 or a place value. So 18,000 is standard form for 1 8/10 times 10 to the fourth power. 2 5400ths times 10 to the negative sixth power. 2 5400ths multiplied by 0.000001. There's another name for 10 to the negative sixth. We'll multiply that by 2 5400ths, and we'll have it in standard form. Using our shortcut, we'll recognize that we are 6 decimal places to the right of our decimal point, which means we can count 6 places to the left. Now note that I'm counting 6 to the left because the exponent was negative. When we do that, we'll represent our product as 0.000000254. And there is the standard form solution that means the same as 2 5400ths times 10 to the negative sixth.
So 2 times 10 to the third. It's a positive exponent, so we're going to move the decimal 3 to the right because it's positive. So we go 1, 2, 3, fill in our zeros. You get 2,000. 6.8 times 10 to the fifth. Again, positive exponent. We're going decimal to the right. So 6.8 times 10 to the 5th would be 680,000. We start with our decimal point there, move it over 5, fill in the zeros, we get 680,000. Let's try one with a negative exponent. 3.25, so 3 and 25 hundredths. It's a negative exponent, so we're going to be moving the decimal point to the left. So you would get 0.000325. Again, we move the decimal 4 places. Let's try this one. Pause the video and try all 3 of these on your own and compare your answers. Now we're going to be expressing the numbers in scientific notation.
So this is Mrs. Workman. Express each number
in scientific notation. First number we're given to rewrite is 520,000. When we write a number in scientific notation, we want to write that number as a product of a number that is greater than or equal to 1 and less than 10 times some power of 10. Now, how do we actually do that? Well, we want to put the decimal point behind the first non-zero digit. And so in this case, that would be right behind the 5. And we'd write that 5.2. Now we need to multiply this by a power of 10 so that it's equal to, when all is said and done, 520,000. Now that power of 10 in this case would have to be 100,000. Now how did I know that so quickly? Because the decimal point would have to be moved 1, 2, 3, 4, 5 places. And there's the 5 zeros. Finally, in scientific notation, the power of 10 is written with an exponent. So that would be 10 to the 5th power. So 520,000 in scientific notation looks like this: 5 2/10 times 10 to the 5th power. All right, let's look at our second example. 0.0006, which is 6 ten-thousandths. And we're asked to write this in scientific notation. Again, we want to write that number, rewrite that number, product of a number that's greater than or equal to 1 and less than 10 times the power of 10. To actually do that, we want to put the decimal point behind the first non-zero digit. So it would be 6.0. And we'd want to multiply that by a power of 10. Now in this case, the power of 10 is 0.0001, or 1/10,000th. And how do I know that so quickly? Because the decimal point was moved 1, 2, 3, 4 places in this direction, which tells me there would be 4 decimal places. Now again, we like to write the power of 10 with an exponent, so that would be 6.0 times 10 thousandths, written in scientific notation, is equal to 6.0 times 10 to the negative fourth power.
So let's write 4 million with scientific notation. So we count. We're gonna put the decimal place here. We want it less than 10, greater than 0. We move it 1, 2, 3, 4, 5, 6. That's how we get 10 to the 6. Try 0.072, 72 thousandths. Okay, so we move the decimal to make the number between greater than 0, less than 10. You get 7.2 times 10 to the negative 2. It's negative because we're moving the decimal to the right. We're writing a small number. Pause the video and try these two on your own. 800,000 into scientific notation, and 119 ten-thousandths in scientific notation.
In 2011, the population of Texas was
674,681. Write an estimation in scientific notation for this population. A population of 25,674,681 can be estimated as approximately 30 million. So what we'll do is write 30 million using scientific notation. The decimal is at the end of the number, and you'll notice we'll move 1, 2, 3, 4, 5, 6, 7 places to the left. In scientific notation, the population of Texas will be 3 times 10 to the 7th power. The population of Texas is about 3 times 10 to the 7th people.
The population of Kansas is 2,853,118 people. Write an estimation in scientific notation. We can round or estimate the Kansas population as 3 million. Then we count. We move the decimal to make the first number greater than 0, less than 10. We get 3 times 10 to the 6 because we move the decimal 6 times to the left. Try this one. The population of Montana is 998,199. Write an estimation in scientific notation. Pause the video and try it out on your own.
whale eats about 2,620
pounds of copepods, a type of zooplankton, a day, or 958,125 pounds per year. Is it more appropriate for a television documentary to report this as about 9.6 times 10 to the 5th pounds, or about 480 tons? Explain your reasoning. We have two choices here. Should the television documentary report 9.6 times 10 to the 5th pounds, or 480 tons. So these are the two choices. The measure of 480 tons is more appropriate. The number 9.6 times 10 to the 5th pounds is very large, so choosing the larger unit of measure is more meaningful. Thank you for using McGraw-Hill Personal Tutors. Welcome.
The space shuttle traveled about 8 kilometers per second. At that rate, the shuttle would take about 4.5 times 10 to the 4 seconds to fly to the moon. Is it more appropriate for the newspaper to report this time as 4.5 times 10 to the 4 seconds or about 12.5 hours? Explain your reasoning. I would say the measure of 12.5 is more appropriate. The number 4.5 times 10 to the 4 seconds is very large, so choosing it would not be as meaningful. People would better understand 12.5 hours. If you could ride your bike 200 meters per second, it would take about 1.92 times 10 to the 6 seconds to ride to the moon. Is it more appropriate to report this time as 1.92 times 10 to the 6 seconds or about 22 days? 22.2 days would be more appropriate. People would be better to understand it.
In this problem, we'll compare numbers in scientific notation.
Population. The populations of 4 cities are shown below. Order the populations from least to greatest. 7.6 times 10 to the 6th, 3.4 times 10 to the 8th, 2.1 times 10 to the 3rd, 3.9 times 10 to the 6th. First, let's look at the exponents. Notice in the first example we have a power of 6, followed by a power of 8, then a power of 3, and finally a power of 6. It says that we want to order these populations from least to greatest. So, our smallest number is going to be the number in scientific notation that has the smallest power. Notice that is 2.1 times 10 to the 3rd. That's going to be our smallest number. Next we compare, and we have a 6, and another 6, and finally an 8. So now we need to compare the 7.6 times 10 to the 6th and the 3.9 times 10 to the 6th. Both have a power of 6, but notice that the 7.6 is greater than the 3.9. Therefore, the next number in our sequence is going to be 3.9 times 10 to the 6th, followed by 7.6 times 10 to the 6th. And finally, we have one number left, which is 3.4 times 10 to the 8th, and that is the largest. So now you've learned to order numbers in scientific notation from least to greatest.
The table shows different geological time periods. Order them from oldest to youngest. We're going to order them by their exponents. The Tertiary period is exponent 7, so it is the youngest period. Order the numbers with the same exponent by comparing the factors. We have 10 to the 8th, 10 to the 8th, 10 to the 8th, 2.45, 4.38, 2.08. We know 4.38 is greater than 2.45 is greater than 2.08. So 4.38 times 10 to the 8th is the largest, 2.54 times 10 to the 8th is the medium, and then 2.08 times 10 to the 8th is the youngest. So our periods would be Silurian, Triassic, Jurassic, and Tertiary. Try this one on your own. The diameters of Neptune, Saturn, Uranus are 4.9 times 10 to the 4th, 1.2 times 10 to the 5th, and 5.1 times 10 to the 4th, respectively. Order the planets from greatest to least.